Okay, so I'm coming from the field of room acoustics, and I'm specifically interested in computational acoustics. And this talk the problem will essentially boil down to what Paul Gogans was talking about, Bayesian filter design. So I'll start by trying to motivate this problem and describe why we think this has a nice Bayesian solution. So the reason we're interested in room acoustic simulation, well, there are a variety of reasons. Maybe an architect wants to design a room and listen to it before, if you're building a concert hall that's several $1 million, it's harder to fix once it's built, easier to calculate beforehand. Auralization is another one. We can, like I said, listen to spaces. It's useful for virtual environments. This is the cave at Aachen. They project onto a screen, and in principle, you can walk around this concert hall or whatever space you're in and listen to it. Also for telepresence, the military has their interests as well. But when we look at, and this is also a typical model that we might consider a concert hall. You can see we have a lot of complex geometries and surfaces. We're interested in solving the wave equation, but our boundary conditions are this, or our geometry is that. So in room acoustic simulation, there are basically two classes of methods: wave acoustic methods and geometrical acoustic methods. And the wave methods calculate wave propagation, or the geometrical methods are sort of asymptotic approximations at high frequencies, and we can calculate ray paths, particle paths, trajectories. The wave methods are relatively expensive to the geometrical methods, and they're typically only feasible at low frequencies because of finite computer memory. And these geometrical methods, like I said, are only valid at high frequencies. And so with the wave methods, we can get things like diffraction interference, which are important for various applications. Maybe we want to look at scattering. And these geometrical methods can be modified to approximate diffraction interference, but then they become more expensive. And so I'm going to focus on the wave acoustic methods. We've got, these are pretty standard methods for solving PDEs. In engineering applications, there's the boundary element method, finite element method. A lot of times these are in the frequency domain. I'm going to be looking at, or I am looking at finite difference methods, particularly in the time domain. They're fairly flexible and simple to implement. Basically discretize the volume, discretize the room, mesh it, evaluate the pressure. The acoustic pressure is typically what we're interested in. Some indexed. We'll have evaluated on the grid delta x, delta t, say in one dimension. Then we discretize the governing equations, either the second order wave equation or the associated coupled first order equations, where we introduce the particle velocity of a differential fluid element. And so just conceptually, if time is over here on our y-axis, and this is our spatial axis, in one dimension we use present and past values to update future values. We can sort of iterate through our mesh and propagate wavefronts. This is fine. Once we get to the boundaries, we have the typical sort of classical boundary conditions. When they're homogeneous Neumann and Dirichlet conditions correspond to rigid walls, pressure release boundaries. But if I'm modeling a room, I want to consider realistic boundaries. This wall isn't rigid in reality. So we have an impedance boundary condition. And this is a complex impedance, and it's frequency dependent. So we have a phase shift in there, and also a change in magnitude. We can look at reflection coefficients and things like this. And so it's typically formulated in the frequency domain. The pressure is related to the velocity here by some impedance function z of omega, angular frequency. We transform it back into the time domain, and we have effectively a convolution boundary condition. And now you might say, oh, this kind of looks like the filter transfer function that Paul was talking about earlier. which leads us to select a model. Typically, to evaluate this, you pick an impedance function that you can, that either truncates this convolution or somehow makes it so it's more amenable to computation. So before I get 3 or 4 z's flying around with different meanings, I'm just going to call the impedance C here, the specific impedance, normalize it by specific impedance of air, which is what we typically do. And then, since we say, oh, this looks like a filter, it is a filter, we're going to model it with the typical standard IIR rational polynomial function in the z domain. And as Paul said, the z's transform back into the time domain as delays, which is useful because with the finite difference methods, we're discretized in time, so there's no further, if we have a frequency domain model, instead of delays, these will transform back into derivatives, which we have to discretize, but the z domain takes it right back to delays and feedbacks. So we have to solve for these coefficients b sub I, a sub I. They're typically normalized by a0. If we want the frequency domain response, we project it onto the unit circle there. And so with traditional filter design, like Paul was talking about, even though it was, this is an infinite impulse response filter, he was talking about finite impulse response filters. They're a little bit different, but you typically have an ideal brick wall magnitude response, and you want linear phase, minimum phase, something. So you're basically designing for the magnitude, and you have cutoff frequencies, and you maybe define a filter order. And then from that, you calculate the coefficients. But for this particular application, we're given some, I might say arbitrary, transfer function or impedance function, which includes, we can't just use linear phase because we want to get the phase shift right if we're modeling, say, a resonant wall or absorber or something like this. Then we have the frequency content of our scheme, the required accuracy of our scheme, and from that, we need to calculate, yeah, the coefficients a sub I, b sub I, but also the model order n here, which to some might suggest a Bayesian solution with parameter estimation and model selection. And so this is what we want to do. We want to use parameter estimation to get these coefficients. We can get them other ways, but the Bayesian formulation also gives us this model selection to choose the order of the filter. And there are 2 reasons for this. One, it eliminates this sort of eyeball norm practice where we say, it's, you know, this function is pretty close to what I have, which we tend to see a lot in the finite difference literature. People say, here's an analytical solution, here's my solution, they have good agreement. I'd like to eliminate that if we can, so we're going to use model selection. And it also, this overparameterization is directly related to memory storage requirements, which becomes an issue. So here we have our model again. This n and m, I have different orders on top and bottom. Not generally equal, but for simplicity, I'm going to say they're equal. But when we go to the implementation, you know, our time, these are our time, this is discretized in time here, each time level there. And as we increase the order here, we have to increase the values that we store on the boundary as we go back, or when we calculate this. And in a room maybe this size, if we want to simulate it up to, say, 500 hertz, which is maybe halfway logarithmically through the audible frequency range, maybe up to where these geometrical acoustic methods are valid, we're going to have on the order of 10 to the 6th points in the volume discretization, and on the order of 10 to the 5th on the boundary. And so if we have something like a 10th order filter, we're effectively storing another copy of our mesh, which is typically the limiting factor in determining, you know, how high frequency we can go and how big the problems we can have and how complicated the geometry can be. So it's important to get, you know, an accurate representation of the impedance, but without superfluous memory storage requirements. So I won't spend too much time on the Bayesian formulation. We assign a flat prior over the coefficient space, and we assign a likelihood here. K is the number of points in our impedance model. We have our squared error, just the difference between the impedance we want and the frequency response of the filter. And as this will come up later, and came up in the discussion in Paul's talk, this may be an area where we need to go back and rethink things. Then we calculate the Bayesian evidence for model selection. And right now we just use importance sampling. We're just getting started in this. And this is maybe gets us to a proof of concept. We've heard about all these other sampling methods, which should perform better. But I'll just go on to here. This is sort of what we get, the frequency response of these different filters. The black line is what we want. We just use a model of the VOLR model for porous materials for a given sample that we happen to have in our lab. And then these are what we get from the parameter estimation. We can see that 17 fits it pretty well, and n equals 13, we're not quite there, but we still capture all this sort of resonant behavior up there. If we look at our evidence, it's on a log scale. It certainly peaks at 17, so we know we don't need to over-parameterize and come out here and store past 17 time steps back. And so to sort of summarize, we're looking at room-acoustic simulation and modeling realistic walls on the boundary. So we use this IIR filter model to represent the impedance, and then model selection and parameter estimation to sort of inject some rigor into the selection of filter coefficients in the models. In the literature, people sort of do everything by hand, and they use filter orders from second order up to 40th order, and things like this for different applications. And so in the future, we obviously need to use more robust sampling methods and look at how we define the errors, as Paul talked about. And the idea in the end is that we can go into a room, measure the impedance of a wall, and then put it in our simulation to hear what it sounds like. We can modify it, etc. And one other thought, since we're looking at, so as suggested earlier this week, since we're looking at such high order filters, it's typical instead of using, say, a 17 order filter, to just use a sum of second order bandpass filters. Sort of like this. If we want to represent this curve, we can use these little bandpass filters here, which also lends itself to the parameter estimation and model selection. You can decide how many of these filters you need to use, and this tends to improve stability and would certainly improve the computational expense. So that's all I've got.
Questions? Udo.
Looking at the model probability, 17 was clearly the best model, but not so far superior that the others have completely vanished. So how about, instead of using model selection, doing model averaging?
Okay. Okay.
And another point, just looking the slide before the model probabilities, it appeared that the higher order models, 23 or so, were even worse performing than the lower order models, and that's something I do not understand, because you have more free parameters.
Yeah, my best guess right now is there are a couple things that could be at play. One, the importance sampling, and we may be getting off there. And the frequencies are linear. And so this low frequency behavior is weighted less than the high frequency behavior. There is a section of, I only went up to maybe 20,000 hertz. There was a little bit after that that could contribute to that too. Maybe it doesn't fit up there. Yeah, you're right. And it, yeah, it's, yeah, okay.
Jonathan, can your system evaluate diffusive surfaces? I'm myself a big fan of the Schroeder diffusers, 1 and 2-dimensional. What would happen if you applied your measurements on a Schroeder diffusing surface?
Apply the numerical method, the finite difference?
Yes.
Well, you could do it a couple different ways. Yeah, people have done it. You either modeled the geometry in which you have to, discretize down to here, depending on the size of your diffuser, or you could sort of do like an amplitude grading diffuser which approximates it, so you have sort of different impedances along here. And if you have a complex impedance, you can incorporate that phase delay. So yeah, it's a reasonable thing to do. Yeah.
Yeah. Can I also join this discussion? The challenges using a wave-based method is really is computational load. If you really want to model the fine roughness, it's fine. But the point is, since we are only interested in low frequency, and the low frequency behavior, most of roughness, you can just ignore it. Right? It's just plain. That's fine. But the point is a very difficult, very complicated impedance curve is really very hard to get. So the other notion to Udo has right, may be right, and he just studied. Jonathan is highly motivated through this Bayesian conference, and especially the John scaling, and talk about for high dimension, nice sampling is no trouble. You just, and he will go back to implement, and then next time we'll show you results. More questions? We have time for questions? Anybody has any? Okay, let's thank the speaker.